Section 1.62, the limits of sequences, we're going to do more examples. But before the example, we are going to mention a theorem, that is the increasing bounded sequence theorem, which says if a sequence is increasing, so it's crawling up, and yet it's bounded from above, so it can't go too high, it just kind of gets higher, and yet it's stuck there to start crawling level, then that sequence has to converge. Similarly, a decreasing bounded sequence, a sequence that goes down less and less, and yet it's not allowed to go down too far. Okay, it start bunching up when it gets to a certain point, and it still is decreasing, but it's not ever allowed to decrease past a certain point. And when that happens, the sequence is a decreasing bounded sequence, and it also converges. The theorem will be proved later in the next chapter. For now, we're just going to look at some examples of it. Let Sn to be the sequence of numbers added up. 1 over 1 factorial, 1 over 2 factorial, added all the way up to 1 over n factorial. And we're supposed to show here that Sn converges. Now Sn is definitely, because each time you go Sn plus 1, so Sn plus 1 is simply Sn added one more term, okay? Added n plus 1 factorial. Each time you slap on another one of these things to create the next element in the sequence. And therefore, it obviously is increasing. So Sn is increasing. However, how do we show that it is bounded? To show that it's bounded, we normally compare it to something else that we know for sure is a bounded sequence. And that's usually how you show this kind of thing. Well, there's more than one way, but usually you have to come up with a sequence that happens to dominate the sequence, and yet still converges. And that's kind of a hunt and fish trick. But for this one, it's very easy because you look at the 1 over n term. What is 1 over n factorial? Well, by definition, it just means this. 1 times 2 all the way up to n, okay? And then what if we will exchange this thing, okay? This goes 2, 3, 4, all the way up to n. We'll exchange it with only 2. 1 times 2, 2, all the way to 2. And it goes from 1 to n. Each number here, we will replace it by 2. And because 2 is less than anything in here, okay, once it go past 2, then this number is less than this number, which means the fraction is going to be bigger. And how many things are here? We're counting from 2 to n. The whole thing has n terms. This also has n terms. So from counting here, it has n minus 1 terms. So this equals to 1 over 2 to the power n minus 1. All right. So then the way we control Sn is to say, then Sn is bounded by this particular relationship. There's actually no equal to 1 past n. But anyway, this is bounded by the relationship of 1 is the same, okay, 1 and 1/2, we will not control it. Starting at 3, and we will start being able to control it, which is 1 over 2 to the second power, all the way up to 1 over 2 to the power n minus 1. Each time this thing will be smaller than the next term. And then 2 to the power n minus 1, as we have shown, is less than 1 over n factorial. So then this is a bounded sequence. Next thing we're going to do is dig out the geometric progression formula. The geometric progression is this thing. If you have this pile of stuff, and it keeps adding all the way to a to the power Rn minus 1, this is by formula equal to this. A times 1 minus R to the power n divided 1 minus R. And the geometric progression is something we've seen earlier. If you don't quite remember it, just believe me. This is what you would dig out if you were to go digging in, I don't know, elementary calculus or something. Anyway, so we'll set A equal to 1. So set A equal to 1 in the formula of the geometric progression, and we get this equation is equal, so Sn is less than, you will have 1, 1/2, and so on. So we have less than, the equation A is 1, so it's 1 minus 1/2 to the power n divided by 1 minus 1/2. And that is the same as 2 times 1 minus 1/2 to the power n. And what is that? Because 1/2 to the power n is less than 1, and it gets more and more less than 1 as n gets bigger, this 1 minus this thing is somewhat less than 1, and therefore the whole thing is going to be less than 2, okay? Because this thing is less than 1. And which means Sn is bounded. Notice that Sn is less than 2 no matter how big n is what we have established, and therefore it's a bounded sequence. We have shown that Sn is an increasing sequence, it's a bounded sequence, therefore by theorem, it is a convergent sequence. We haven't figured out what it converges to, but for this problem, we're not interested in that. We're just trying to show that it does converge.